today we're going to start Chapter 3 off with Section 3.1, which is going to get us into functions. So let's look at what some functions are. Functions are going to talk about, we're going to look at defining a function, looking at domain and range, and then looking at function notation. So getting into a couple definitions for us here, domain, range, and a function. Domain, you can see there, that's the input, the independent variable. Think of these as the x values. We talked about that last chapter. The range is going to be the output. That's the dependent variable. Again, we talked about that being the y's from the last chapter, the y values. So a function there, you can read that. Key part here is italicized. Each element in the domain, there corresponds one and only one element in the range. So what that means, if you have more than one x value, it's not a function. What I mean by that, more than one of the same. I should put that in there. More than one of the same x value, it's not going to have. You're not going to have a function. So a couple examples here. We'll start off with this is just some general ones with a couple charts here. So looking at these, I have these two tables. Called this for this first one is called this network. Call those the x's. Call the viewers the y's. If I'm looking at this as my x's, none of those repeat. So yes, this is a function. If I was looking at talking about the domain, this right here would be the domain. The x's, all the x's listed would be the domain. This right here would be the range. Looking at the second table, again looking now at calling these the x's and these the y's. Looking here, the Toyota is the same. Same with the Honda. Honda repeats. So therefore, this is not a function. And we don't have to worry about the domain and range if it's not a function. We can just go ahead and move on. So the second example, getting into some ordered pairs, looking at domain and range with the ordered pairs. So the first, we'll examine this. Again, 1, 2, 3, 4, and 5 are all my x values. None of those repeat. So letter A is a function. And if I'm looking at the domain, I would just list all those values. 1, 2, 3, 4, and 5. Not the comma. The range the same way. Now, I do not want to repeat. Remember back to chapter 1 talking about sets. Really, I think it's part of chapter R as well. We don't want to repeat the numbers. So 4, 3, 2, 3, 4, I would just put 2, 3, and 4. The order isn't very important, but I put them in order just because. For letter B here, 1, 2, 3, 2, 1. So this is not a function because again the 1 and the 1 repeats, the 2 and the 2 repeats. So again, letter B is not a function here. Moving on into graphing, we're going to decide whether these are functions or not. So what we have to do here, again, I have both of these, and then it's a lot easier to pull up Desmos here. So you can here's the first graph that you can see. And looking at this, you can see that if I would go over here to this point right here, this is 8, 3. And if I come down here, this is 8, -3. So if I were to list out all the ordered pairs of this graph, I would find out that 8, 3 and 8, -3 have the same x value, making this not a function. So we would not say that's a function. Here's the second one. Let's turn that one on. Same type of thing. It's a different graph, but again, if I can scroll my pen here, my cursor, and find out that this is, I can't get quite on -2, but the same premise is if I'm going to list off all the values that are on the graph, I'm never going to get any x values that repeat. I'm going to get close. Here's positive 0.7. Over here is going to be negative 0.7. But again, that's a positive negative version of the same number, which is not the same number. So this would be a graph. This would be a function. Excuse me. Talking about the domain and range of this real quick. As we look at this graph, as it's getting taller and taller, it's getting wider and wider. So what we can say about the domain of this graph, let me get back to the PowerPoint here, if I can. So looking at the PowerPoint again, this was the parabola that went up and up and up. So the domain of this, the x values, I'll try to go back and forth quick. The x values of this, they're going again, it's getting wider and wider, wider and wider. So the x values there are going to be, if I can get this back up again, the x values of this graph are going to be all real numbers, from negative infinity to positive infinity. The range, however, that's going to be a little different. So again, glancing back at the graph, this is the lowest part of the graph. So it's 3.33. So the range, it goes on higher and higher from 3.33. So the range is going to be not all real numbers because it doesn't go below 3.33. So it's going to be everything that's 3 1/3, or we'll call it 10/3. So we could say the y values are going to be greater than or equal to 10/3. Or if I'm looking at this as an interval notation, it would be 10/3 to infinity, including 10/3. So that's how we like to think about the domain and the range of both of those, whether or not they, just looking at whether or not where they start, where they go, where the x values go to, where the y values go to, and so on. So again, there's the vertical line test. An equation is a function if and only if a vertical line passes through it at most one point. So again, back to the graphs real quick. A vertical line is not going to pass through, if I would draw vertical lines, it's not going to pass through this graph anytime more than once. Whereas this first one that we did, a vertical line would pass through this graph twice every time we drew a line. You should be familiar with a vertical line. So these last two graphs, again, have both of these. If I drew vertical lines, I'm going to get, the vertical line is going to hit the graph both times. So those are both not functions. So getting into finding the domain and how we find the domain, if it's not given and we don't have the graph, we assume it's going to be the set of all real numbers. So if generally we can look at it, if it's a polynomial, it'll often be all real numbers. But if it's not, that's when we got to think about it. So we've talked about this before. We got to think about what makes this a real. We're talking about real numbers here. So number 7 there, what would make this not a real number? And we know that what makes that not a real number is when I have a negative on the inside of the radical, in the radicand. So I would say x minus 3 has to be greater than or equal to 0. So x has to be greater than or equal to 0. So our domain here, our x values, will be x is greater than or equal to 0. And you guys all know that that is 0, infinity in interval notation. Looking at number 8, are there any values of x that I can plug in that are going to make this an imaginary number or non-real number? And there aren't. This is a good polynomial, so this is just all real numbers, or negative infinity to positive infinity. For number 9, what would make this not work is if I get a 0 on the bottom. So again, the x value, so I'd say x minus 2 cannot be equal to 0. X cannot be equal to positive 2. So this is a little different. This is all real numbers not equal to 2. And in interval notation, we're familiar with this. I'd say negative infinity to 2, union 2 comma infinity. And again, I cannot include 2 because 2 would make that 0 on the bottom, and that would not be good for us. Function notation now. So we have been familiar, especially with last chapter, which you just took the test over. Function notation is generally looked at, or the general coordinate notation is x comma y. Function notation, we are going to replace the x with an f of x. An ordered pair, so this takes the place. So think of f of x is the same as y. That's our y value. It's going to be the domain. So if x is in the domain, it doesn't exist, but we won't talk a whole lot about that. So we'll just focus on function notation. So what function notation is going to do? It's going to find, these examples are the best way to explain it. It's just find the indicated values here. So this is function notation. F of x equals 4x minus 3. So I want to evaluate for f of 0. So what I do with f of 0, what I do with the 0 is I'm going to plug it in for the x. So it would look like this. F of 0 equals 4 times 0 minus 3. Now, f of 0 is just a value. That's telling me what I plugged in and am evaluating for. So f of 0, 4 times 0 is 0. 0 minus 3 is negative 3. So this now gives me an ordered pair. My ordered pair here is 0, comma, negative 3. So with function notation, we can easily find out what our ordered pairs for this particular function are. So I'm not going to go through all of these. I'll do a few. Let's do f of 2 now. Plug in 2, so f of 2 equals 4 times 2 minus 3. 4 times 2 is 8. 8 minus 3 is 5. F of 2 is 5. And again, my ordered pair there would be 2, comma 5. One last one there at the bottom. F of a. I would just plug in a. F of a equals 4 times a minus 3. F of a equals 4a minus 3. Now these other ones, this g of 9, g of negative 9, g of 0, I know where to plug this into because this is g of 0. I'm not going to plug in the g of 0 into the f function or the k function for that matter. I'm going to plug this g of 0 into the g function. So the variables that are before the problem in function notation, those are important, so pay attention to those. I'm going to skip over these for now and look at number 16 with k of x. So we want a value for k of x plus h. So this tells me I'm plugging in x plus h in for the x values into the equation. So it would look like this. K of x plus h equals x plus h quantities squared plus 4 times x plus h plus 5. So again, k of x plus h, we know how to evaluate this. Again, this is not x squared plus h squared. We know that how bad that is. So we know shortcut x squared plus 2xh plus h squared plus 4x plus 4h, add some h, plus 5. Combiner-like terms, I really don't have any, so this would be my final answer. So again, whatever the value you're looking for to evaluate, you're plugging that in for the different values of x. That should wrap up the lesson for today. Thanks.